Okay, so if you look at this equation, all I did was take the ideal gas law equation, P1 V1 equals nRT, and this is typically what happens with gas laws when you make comparisons based upon temperature, volume, so on. If you get this, this will probably solve about 95% of all gas law equations right here. Assuming that the number of particles stay the same, you're not going to change the number of TIVs in the classroom. You're not going to change the R because that's the gas law constant, okay? So those aren't going to change. So what this allows you to do is compare pressure, temperature, and volume in two different situations. So the beauty of this is that because it's a ratio, the pressure and volume just have to be in the same units. But the temperature, listen to me, listen to me, listen to me, listen to me. This only works if the temperature is in Kelvin, okay? You cannot, under any circumstance, using any gas law problem, leave a temperature in Celsius, okay? It will not work. Every temperature has to be in Kelvin. Pressure could be in atmospheres, volume could be in liters, cubic meters, doesn't make any difference because it's a ratio. But the temperature, absolutely, no exceptions, none, zero zip, has to be in Kelvin. What?
What about Rankins?
Just don't. Okay? It's got to be in kelvins. All right, so let me give you a simple example. So let's say that you've got a cylinder that has a volume of, we'll make the math easy, 1 cubic meter, and that's under a pressure of 2 atmospheres. Now, if you're really hardcore, it's like, Bergkamp, I live for the MKS system. You could do this and you could change this into atmospheres and go 1 atmosphere is 101,300 newtons per square meter, which is the same thing as a Pascal, okay? But if you look at how this is going to play out, what I want to know is what's going to happen if the new set of conditions is that I increase that new pressure to 4 atmospheres. Now I want to know, okay, hey, what's going to happen to the volume? So when it goes from 2 atmospheres of pressure to 4 atmospheres of pressure, and I want to know what's going to be the new volume. So here's how you use this equation up here. So in this situation, I'm keeping the temperature the same. Temperature is a part of the story. So I'm going to cover up the temperatures. Okay, I don't need the temperatures. It's not part of the story. Because no matter what the temperature is, that's going to be the same on both sides of the equation. So I don't care what it is because it doesn't matter. It's not part of the story. So what that leaves me then is P1 V1 equaling P2 V2. Now, because this is just a ratio, I can leave this in newtons, I can leave it in atmospheres because I would multiply both sides by 101,300 and that would itself cancel out, okay? So because it's a ratio, I can leave it in newtons per square meter. Now, if you are actually dealing in a situation where you have PV equals nRT and you have a certain number of moles and temperature and you want to find a volume, that absolutely has to be in newtons per square meter. If you're dealing with one equation, and you're just dealing with PV equals nRT. But if you're doing with a comparison, as long as it's the same thing, that's all that matters. All right, now, if you look at this, you had pressure 1, which is 2 atmospheres, and you had a volume of 1 cubic meter. So Connor A, I'm going to increase that pressure to 4 atmospheres. So what's going to be my new volume? What'd you say? No. There's nothing squared on this whole deal. Do not make this difficult. You're making this difficult. Yeah, 1/2, okay? That's it, it's just gonna be a half, because of this equality sign, these two sides have to be the same. So check my math, if you take 2 times 1, you get 2. So over here, that side has to equal 2. So therefore, it's basically what times 4 equals 2? Oh, that's a half. Now, if you don't believe me, it's like, oh, Bergkamp, that's voodoo. Well, fine. Divide both sides by 4. 2 divided by 4 is a half. Boom, there you go, okay? Now, if you think about it, that makes sense. So, basically what we're saying is this. You have a room full of second graders. We're not going to change the number of Timmies, and we're not going to change the amount of Skittles that the kids have. No Skittles are allowed in or out of the classroom. So, imagine this. You're teaching this class, you're interacting with these little ankle biters, and they're running around. And we're going to take the pressure inside of this room, and the only way we can make that pressure change is by changing the size of the classroom. Well, if I want to have more collisions with my ankles, what am I going to do to the volume of the classroom? Make it bigger or make it smaller?
Make the classroom smaller.
I want to make it smaller. So when I shrink the classroom, my ankles are going to have more collisions with the ankle biters. So therefore, I will feel more pressure because of the fact that I'm going to have more ankle biters around. And by the way, thanks to Mac's mom, I got to do that. Next week, go to Vermilion and read to the little ones. We'll talk about that because I want to have like a group prayer at some point. So either for me or for the kids, because bad things are going to happen. Okay, all right. Now, on the bottom of this sheet, and I will give you these if you need them, you have these equations. It's got L equals L naught 1 plus alpha delta T, and then you have delta L equals L naught okay. Now, so let's talk about these equations. So these give you either the volume, the amount of linear expansion, area expansion, or volume expansion. So on that sheet, and no, don't memorize it, I will always give you the sheet, that constant sheet. You have different values of thermal expansion, but it's a weird deal in terms of the units. Because if you look at this value of alpha, and no, that is not angular acceleration, okay, that's just alpha. It's a completely different alpha. That has units of Celsius to the -1, which means the inverse of Celsius. Now, this is why this works. First off, notice on all of these equations that is change in temperature. That is not the temperature. This only plays out when the temperature changes, okay? So, and because it's change in temperature, if you go from 20 degrees Celsius to 30 degrees Celsius, oh, that's 10 degrees Celsius in terms of change. If you have Kelvin, that's 293 Kelvin, and that's 303 Kelvin, which is still 10 Kelvin. So, because it's a change, whether you're in Celsius or Kelvin, it doesn't make any difference because it's a change in temperature. So, mathematically, this is why this works. So let's say that you have a certain length of board. I don't know, 5 meters, okay? So that would be your L naught value. That would be that initial length. And let's say you heat it up by 10 degrees. So what you've got to do is you've got to look on your sheet and you have to find out what that material is. Iron, brass, steel, whatever that is. They all have different coefficients of expansion. But the units for that, so you've got your L naught, which is 5 meters, and you have 1 plus, and you have something in Celsius to the -1 times Celsius. Well, the Celsius cancels out. This has no units, so you're taking something that has no units and multiplying it by meters. So when you multiply something that has no units and multiply it by meters, what units do you still get? Meters. This is the only time I will ever tell you. It doesn't make any difference what units these are in. Okay, it does not matter. It could be in centimeters, it could be in meters, it could be inches. Doesn't make any difference. Because mathematically, it's all treated the same. But here's what's important. The bigger that temperature change is, the bigger that value is going to expand. Okay? So, if you look at this in terms of area, why do you think on area we have a 2 in there? Oh. And in volume, we have a 3 in there.
How many dimensions?
Yeah, area has 2 dimensions, therefore we have a 2. Volume has 3 dimensions. Okay. Now, I know you maybe Southeast have to go. There's one other equation that you're going to need to know.
Where's that cue? Where did that cue come in?
Okay,
Oh, yeah.
so what this, write this down because you need this for the last problem on your assignment. So this Q is energy, okay? This is time in seconds. So when you divide joules per seconds, what do you get? Watts, okay? So this is watts. So this is how much energy flows per unit of time. This value of K, and you need your textbook, and on the assignment I tell you, this is on page 385. This has different units values based upon the units. So if you look on page 385, like air, for example, has a very, very low thermal value, which means air doesn't conduct heat very well. Metals conduct heat very, very well. So this is your area, this is your change in temperature, this is the thickness. So what this does, if you look at, like, let's say, for example, a Stanley Cup, ironically, okay? So why do people, this is become all the rage, why do people have these cups? What do?
Does insulation effects.
Right? What this does is that it minimizes this value, okay? You don't want stuff to cool down or warm up quickly. So you have a very, very big K value. Glass, metal, but there's times when you want things to heat up quickly. So you want to make macaroni and cheese, you put a metal pot on the stove. Oh, you want that energy to come across very, very quickly. Okay, so let me hand out that assignment right quick. And I'll turn you all loose.
What is K? Wait, so what's the unit on K?
It's like watts per meter squared Kelvin.
So that's like the constant of what?
It's just, yeah, it just changes.
Hey, you can get that right now.
It'll say.
L is
L is.
Multiple times.
Wait, so that's